So what is it that all of these situations have in common? Well, when I have my bar magnet and I move it close and away, what I've done is I've increased the flux as I move toward the coil and decreased the flux as I move away from the coil. If I have my electromagnet, it's the same situation. It's just not a permanent magnet. If I have my coil on the inside and I turn the current on, well, as the current turns on, it increases the field. And when I turn the current off, it decreases the field. And I turn the current on, it increases the field. And I turn the current off, it decreases the field. And if I switch the direction of the currents, same sort of situation. So I end up with an idea that it's the change in magnetic field, but not just magnetic field, but magnetic flux. And if we think back to magnetic flux, if I have a surface, if I have a magnetic field, say in this direction, like this, and a surface through which it's going through, if it's perpendicular, then it's just BA. But if it has some angle associated with it, like this, I need the normal line. From that normal line, I have an angle, and that angle would be theta. So the magnetic flux, if I remember, is phi b is equal to BA cosine theta. And what's inducing this EMF is the change in magnetic flux, which could either be a change in B, right, or a change in A, and that would be this vector A. So that vector A could either be I could actually deform or change the area of the surface, or I could rotate it in the magnetic field, changing the effective perpendicular area. So if I had, say, a loop that I could deform, I could change the area, or if I rotate an object like this within the field, I end up with a maximum A when the surface is perpendicular to the magnetic field and a minimum when it's parallel. And the relationship that induces this EMF is called Faraday's law. And Faraday's law says that the induced EMF is equal to delta phi b over delta t. All right, so it's that change in time. And we're going to see in another video an example of a problem using this. And that's Faraday's law, and it gives me the magnitude of the induced potential. Lenz's law tells me the direction of the currents, and it says that it induces currents in the conducting surface that oppose the change in flux. So let's say I have a conducting surface here, and I have a magnetic field out of the board, and it is increasing with time. So if it's increasing with time out of the board, I need to induce charges that produce magnetic fields that are into the board. So that would be, so out of the board, into the board, using right-hand rule. I'd induce currents in this direction. Now, if so this is increasing out of the board. If my out of the board was decreasing instead of increasing, so let's say I have decreasing out of the board, well then if it's decreasing out of the board, I want to oppose that decreasing change, so we need to induce currents that are producing a magnetic field out of the board, so I'd actually induce currents in this direction. So you can see how it can get a little bit complicated, because I not only need to know what direction the magnetic field is, but whether it's increasing in that direction or decreasing in that direction to determine if I'm inducing currents in a specific direction. So that's our introduction, and we'll do an example problem in another video. All right. Thank you guys for paying attention.